Welcome! In this episode of Zero to Autonomous, we are going to talk about command-based programming. Today, instead of using a physical robot, we will be programming this elevator bot I made in a simulator. By the end, you'll learn how to program the drivetrain, elevator, intake, and an autonomous sequence in the command-based structure. Let's get started! In the past few videos in the series, we've always used the timed robot code structure, which has an initialize function and periodic function for each robot mode. And in the past few videos, it has been fine because the projects were relatively small. But as we create larger projects in the future, we'll need the command-based structure. So, let's look at how to convert a timed robot into a command-based robot. If we had made the robot in a time-based structure, this is what it would look like. At the top of robot.java, we create all of our motors, sensors, and constants, etc. And we can see the first part is just for the drivetrain. There are 2 motors, 2 encoders, an encoder conversion constant, and a helpful method to quickly get the encoder value. The next block is all about the elevator. We have a motor, a PID controller to move the elevator up and down, and again, we have some stuff related to the encoder. Finally, there's the intake, with 2 motors. Now, these mechanisms don't have that many motors or sensors, so it looks okay if we put them all in one file. But if each mechanism had a lot more stuff, it would make this file very long and unreadable. So wouldn't it be nice if we can create a file for each mechanism and separate all the setup into each mechanism's individual file? This is exactly what the command-based structure does. In fact, these files are called subsystems. For this robot, we have the drivetrain subsystem, elevator subsystem, and intake subsystem. Next, let's look at our teleop periodic function in this timed robot. Remember from the previous videos, this function runs repeatedly during the teleoperated control mode. At the top, we have a block of code to move the chassis using arcade drive. The next block of code controls the intake. It has 2 modes. In the mode where button 5 is pressed, it closes the intake. Otherwise, the intake will remain open. Then, the next block of code deals with the elevator. It again has a few possible types of actions. If button 1 is pressed, it will raise the elevator to 1.2 meters using PID. Button 2 will tell PID to bring it back down. Here, we are using the PID controller from the WPI library. First, we set the set point. Then, the calculate function takes in the current sensor position and returns the PID output. Buttons 3 and 4 are for backup. If somehow the sensor cable breaks or the PID doesn't work somehow, we still have a way to manually move the elevator. Finally, if no buttons are pressed, the default action is to stop the motor. Now, notice how each box contains one action that a mechanism can use. Right now, each action is really simple and only takes a few lines of code, so this is okay. But imagine, if in the future we have a complicated action that has a few hundred lines of code, it would be really messy to put them in these if statements like this. Also, notice how we are writing some code many times. I wonder if there's a way to factor out these actions so we only have to write them once. To solve these 2 problems, we can try putting each type of action into its own file. In command base, these files are called commands. Alright, let's look at the autonomous mode for this robot, and how we can combine different existing commands to construct an autonomous routine. The goal for autonomous is to drive forward and pick up this box. In autonomous init, we will set the distance we want to drive to, which is the current distance plus 1.5 meters. In autonomous periodic, we will repeatedly check if we're there or not. If we are not at 1.5 meters, then drive forward. Once we get there, then stop. We can sort of see this as a kind of action as well, an action that drives forward for 1.5 meters, then stops. So let's put that into a command file. Okay, after we have stopped, we want to close the intake and raise the elevator. Oh hey, we have already made a few commands to do those things, so maybe now we can just use them. Now, let's think of this in terms of commands. We want to first run drive forward command, and when that's done, simultaneously run intake set command and the elevator PID command. So, we can put these two commands in the parallel command group, and then put the drive forward command and this parallel command group in the bigger sequential command group. So these are command groups. They can run multiple commands in parallel or in sequence. Okay, to recap. The robot has 3 subsystems, which sets up the motors and sensors for easy use by the commands. Then, we have 5 commands. Each describes an action that can be performed by the 3 subsystems. And the commands don't have to worry about the hardware details, such as which ports the motors are connected to. The subsystems handle that, and commands can just use them. By putting actions into command files, we are also making them into building blocks, which we can then group into more complex actions. Here, we first group elevator PID command with intake set command in parallel to make a pickup box command group. Then, we combine drive forward command and the pickup box command group into another command group which will automatically start during the auto period. And in the teleoperated mode, we can set up some joystick buttons to trigger these commands. So that's it for the theory. Let's start writing the robot code by making the subsystems. First, we are going to create a robot project. This time we'll select Command Robot. Once everything's created, we can see that there's a few more files here, and we'll talk about those later. For now, to create our subsystems, we want to go to the Subsystems folder. There's already an example subsystem here, and we'll rename it to Drive Subsystem. Notice that this Java file is a subsystem because it extends subsystem base. So, like mentioned before, we are going to just paste in all the motor and sensor setups here, like this. And because our commands will later on use this subsystem, we'll also create a function to easily set the motor outputs. As for the class constructor, we don't have anything to put in here this time. But if you have other setup to do, such as inverting the motors with sensors, they can go here. Another function here is the periodic function. It's really similar to the robot periodic function, which runs repeatedly regardless of which mode the robot is in. But now, we have one of these in every subsystem that we can use. And for now, we can send some debug information to the smart dashboard in here. We won't be using the simulation periodic function, and the subsystem is done. Next, let's make the elevator subsystem. So we'll create another file in the subsystem folder, and make sure to extend subsystem base. Again, we can paste in all the motor and sensor setup. And like before, we'll add another function to set the elevator motors. Finally, let's send the encoder debug information to the smart dashboard again. And that's it for the elevator subsystem. Now, for the intake subsystem, nothing new here. Create a file, extend subsystem base, paste in the setups, write a function to use the motors, and that's it. Great! We have all of our subsystems created and ready to use. The next step is to write the commands. To do that, go into the commands folder. There's already an example command here, and once I clean it up, we can see there's 5 functions. Let's compare that to our timed robot example. There, we were saying, if the robot is in this mode, then just run this line of code repeatedly. That's what the execute function does. When this command is running, the execute function will be called repeatedly. However, we have a few more features here. For example, if there's some setup that we have to do every time before this command starts, we can put it in the initialize function. If there's some last-minute things we have to do before the command ends, we can put it in the end function. So, the initialize function, execute function, and end function make up the whole life cycle of a command. Also, as this command, you can tell the robot whether this command is finished running or not. If this command has finished, the next command can take over. There are two ways a command can be ended. First, the command itself can decide that it's done by returning true in the isFinished function. Another way is something else can interrupt this command, and we'll talk later about how that can happen. But we can see now that the end function actually tells us why this command has been ended through the interrupted variable. Alright, let's implement the elevator joystick command in this file. First, we'll rename the class. Here, we want to use the elevator subsystem that we've already created. However, we don't want to make a new instance of it in every command that we have. Instead, we only want one instance of every subsystem, and put it in some central location. We'll look at how to do that later. For now, we are going to assume that whoever will create this command already has access to that single instance of the elevator subsystem. And here, we can just ask them to give it to us in the constructor. Another thing we are going to add in the constructor is the speed variable, how fast to spin the motor. This way, our command can be reused to operate at any motor speed just by changing this variable. Now we can fill in the rest of the functions. In execute, we will set the motors to the desired speed. In end, we'll stop the motors. IsFinished is set to false, so this command never ends unless interrupted. And we can add some debug information in initialize and end as well. One last important line of code we need to add in the constructor is the addRequirements function. This tells the robot that this command uses the elevator subsystem, and that all other commands that use the same subsystem should be interrupted and stopped before this one starts. Great! Now we are done creating a command. Let's see how to set up a joystick button to trigger this command. The central place to put all of our commands and subsystems is the file robotcontainer.java. Here, we will create one instance of every subsystem, like this. And if I clean it up a little bit, we can see a function called configureButtonBindings. This is the central place to link joystick buttons to commands. On top, let's first create a joystick. Then, in this function, we can make a new joystick button object. It wants to know which joystick this button is on, and which index is the button. And then, if we scroll through its functions, we can see it has a lot of triggers. For example, while active once starts a command when the button is pressed, and interrupts it when the button is released. In between, it does not restart the command repeatedly. This could be something we want. When we press the button, it will start elevator joystick command. The command will keep running until someone interrupts it. So when we release the button, the trigger will interrupt our command, stopping the motors. So we can write new elevator joystick command. And it wants the elevator subsystem and the speed. Fortunately, we have all the instances of our subsystems right here, so we can just pass it through. And we can set the speed to be 0.5. Now, we can create another joystick button on a different button index. Use the same command, but have it operated in the opposite direction. So that is the entire process of creating a command. Alright, now let's create another command, the elevator PID command. First, create a new file under the commands folder. Remember to extend command base to turn this generic Java class into a command that the robot recognizes. Again, we will have the same 5 functions. In the constructor, we will ask for an elevator subsystem instance, and this time, a setpoint number for the PID to go to. We can store the subsystem in a variable and create a WPI PID controller using the setpoint and some PID constants. We will also make the elevator subsystem a requirement of this command to stop other elevator commands when this one is running. In initialize, we'll call PID controller.reset to clear any leftover integration term from the last time this command has run. In execute, we can give the PID controller the current encoder value and get the PID output speed. Then, set the motors to that output. In end, we'll stop the motors just to be safe. And in is finished, we'll return false, so this command runs forever until interrupted. And we can add some debug info as well. One important thing to notice is that although both the constructor and the initialize function are for setting things up, the constructor runs only once when the robot powers on. On the other hand, the initialize function runs every time the command starts, so that's every time we press the button. Since we don't need a new PID controller object every time, we can create it in the constructor. However, PID controller.reset needs to run every time we press the button, so it should be in initialize. Now, going back to robotcontainer.java, we can link some buttons to the elevator PID command like this. So that button 1 moves the elevator to 1.2 meters, button 2 brings it down. Next, we'll make our drive forward command. Let's create a new command file, and this should look familiar. We will ask for the drivetrain subsystem and a distance value. We'll save these values in some global variables and require the drivetrain subsystem. Because the same instance of drive forward command can be run multiple times, we want to make sure we drive that additional distance every time it is used. To do that, we'll add an encoder setpoint variable to keep track of how far we need to go in this current run. In initialize, set it to the distance plus the current encoder reading. In execute, we drive forward at half speed, and in end, we stop the robot. In the isFinish function, this time we will return true to have the command finish once we are at that distance. So later, when we put this command in the sequential command group, once this command finishes, the next one will start running. And it's always good to add some debug info as well. Now, the arcade drive command. Here's a new file, and we can import and require the drivetrain subsystem again. However, when asking for joystick inputs, we can't just use doubles like before, because once they are passed in, they become static and don't change with the real-time joystick inputs. What we really want to do is pass in 2 functions that get the latest joystick inputs, and then run those functions every time in execute. Those functions are called suppliers for doubles, because every time we call them, they give us a double. Now, in execute, when we're implementing arcade drive, we use the .get method of the suppliers to rerun those functions to get the latest values of the joysticks. And again, set the command to never finish and add some debug info. Finally, we have the intake set command. Again, new file, import the intake subsystem, require the subsystem, ask whether to open or close the intake, set the motor in execute, have the command never finish, and add some debug info. Back in robotcontainer.java, we will link this command to button 5. One more thing we can do is to set some default commands to each subsystem. For example, button 5 closes the intake, but when button 5 is not pressed, we want the intake to default to open. So, when setting up robot container, we can write intake subsystem.setDefaultCommand and a command to open the intake. For the drivetrain, the default can be arcade drive. So we create a new arcade drive command and pass it two functions that get the joystick speed and turn axes. In Java, this is a shorthand way to create functions that return the values of these methods. For the elevator, if no commands are present, we can run a new one with the motor stopped. Okay, now let's create a command group to construct the autonomous mode routine. If we scroll down in robot container, we can see a getAutonomous command function. When the robot starts autonomous mode, it will call this function to ask what it should do. Here, we can make and return the command group we want it to run. There are a few ways to make a command group. Today, we'll just create one right here. First, we want a new sequential command group, as it can run some existing commands in order. We will put the drive forward command first. Alright, but for the next two commands, we actually want to run them in parallel. To do that, we can surround them in a new parallel command group. So when autonomous mode starts, the sequential command group will run the drive forward command to drive to 1.5 meters. And when that's done, it will run the parallel command group, which will trigger both the intake command and the elevator command at the same time. Great! Now let's return this whole thing. Okay, by this point, the robot code is fully functional, but there's one last thing we can do. You see, there's a lot of numbers scattered around in this file. For example, this 1.2 makes the elevator go to 1.2 meters. And that's fine until one day maybe the robot drive team tells us to change it to 1.3 meters. Then, we need to hunt down and change every occurrence of this number in this entire project. And that's really easy to mess up. So, what if we group all of these numbers and put them in one central location so they're easy to find and change? That is what constants.java is for. Here, we can define a nested class just for the elevator mechanism. And all the numbers related to the elevator goes in here. So we can define the number 1.2 in here as the k raised position. Back in robot container, we will reference this variable. Next, we can also include the motor port, encoder channels, encoder constant, PID constants, and some driver preferences here. And we can do the same thing for the drivetrain subsystem, intake subsystem, and for the joystick button mappings as well. Finally, we'll replace all the scattered numbers in the robot project and reference them to here. Okay, that concludes the robot code. Now let's run it in the simulator. To download the RobotSim simulator, go to this link. If you're on Windows, extract the zip file and run the .exe file. You can already drive around using the default code, but to run your own code, download robotlib. Go to this URL and unzip the file. To import a real robot project into the simulator robotlib, copy your entire SRC folder and paste it into robotlib. Now, open robotlib in Visual Studio Code. And everything you wrote in the real robot project also magically works here. Finally, to run your program, click Run in the main.java file. And you can see a driver station appeared, and a smart dashboard automatically popped up. Now, let's start autonomous mode and see it pick up a cube. And for teleop mode, focus on the simulator window to operate the joysticks. For more tips and tricks, such as changing the camera view angle, showing debug information, and enabling 60 frames per second, check out the documentation. I hope you have enjoyed this video of Zero to Autonomous, Hit that like button if you learned something new. And until next time, happy coding!